Hello, Chemistry 11 students. This is Mr. Chan. And today what we're doing is we're going to do part 2 of the Lewis dot structures. Now, one thing you need to be aware of is when I taught you the Lewis dot structures, it gives you the basic foundations of what molecules will look like. But there are a lot of exceptions, okay? So Lewis dot structures is not the end-all be-all, but it gives a framework for chemists to figure out what molecules look like. And so today, what I want to do is go over a couple of the exceptions to the Lewis dot structures, okay? Now, I'm just going to share a screen here. Come on, share screen. Here we go. Okay. Now, so what you should have is you should have this set of notes, okay? Now, there are exceptions to the octet rule. And the first one I want to talk about is something called incomplete octet. Now, for an incomplete octet, okay, what we have to do is the central atom can have an incomplete octet and are considered correct. Now, what do I mean by this? So let's say we do boron trifluoride. Now, for boron trifluoride, what you've done is you know that there are 12 pairs. And that goes back to the Lewis dot structure, how to figure out Lewis dots, the number of pairs, etc. And what you would get is you would get a formula of something like this. Okay? And if you were to take a look and draw the lone pairs, it would look something like this. Okay? Now, I use circles. Some of you might use X's. I'll use both. Doesn't matter. Now, this would be considered correct. But you might say, well, for boron, what the fluorine? Okay? It only has 3 pairs or 6 electrons. Mr. Chan, I thought you said that they always have to have 8. So what's the situation here? Why? Well, it has to do with the central atom, and it has to do with the number of valence electrons. Now, for boron, if we were to do the electron configuration, it looks something like this: 1s2, 2s2, 2p1. Notice it has less than 4 electrons in the valence shell. Therefore, cannot fulfill octet rule. Okay? So because there's only 3 valence electrons in the outermost shell, it doesn't have the magic number of 4, and so as a result, it cannot have a full 8 electrons. Now, again, we look at this because of the central atom. I'm not worried about fluorine. I'm not worried about the fluorine that's around. I'm just looking at the central atom, in this case, of boron. Now, the opposite side is talking about expanded octet. And again, the key word is the central atom. In this case, is able to have more than 8 electrons in the valence shell. Now, why? Because if we take a look, okay, in the first 2 rows of the periodic table, the s and p orbitals are the ones that are filled. But in the 3rd row, or the 3rd period of the periodic table, the d subshell is available for bonding. Now, what do I mean by this? So let's say we have ClF5, all right? Chlorine pentafluoride, okay? And so what you have here is you have 21 pairs of electrons. Okay, So if we did the Lewis dot structure, it'd be chlorine. Oopsie. It would be chlorine in the middle. And you would have fluorine all around the side. Okay, and we have, if we draw this, okay, we draw this all around, yada, yada, yada. I've drawn 20, okay, but there's one more pair around chlorine. So the question is, what's the deal about Cl? Why is chlorine able to have more than 8 electrons? Okay, and again, we're looking at the word of the central atoms. Okay, so it has to do with the electron configuration of chlorine versus, let's say, fluorine. Now, if we look at fluorine, fluorine is 1s2, 2s2, 2p, 5. Here, for chlorine, it'd be 1s2, 2s2, 2p6, 3p, like here. Now, but notice for chlorine, this 3D is available. Okay, here, there is no 2p, 2d orbital. There's nothing. And so this is why for chlorine, if it is the central atom, and the key thing is that it's the central atom, it can have more than 8 electrons because of the fact that it has a 3d orbital. So in the third orbit, or third energy level, there's an S, there's a P, there's a D. For fluorine, if fluorine's a central atom, it can only have 8 electrons because there's only a 2s and a 2p. Okay, so it all really depends on the electron configuration. Now, again, we're dealing with the central atom. Notice I highlighted it, okay? The central atom can have less or more depending on the arrangement. But if it is not the central atom, like in this case, fluorine is not the central atom, it can only have 8 electrons. Okay, so again, it applies only to the central atom. All right, another one is resonance structure. Now, when there is no one structure that's adequately represents the molecule. Now, for example, let's say SO3. So SO3, if we take a look at it, can look like this, or it can look like this, or it can look like this. So what happens is, in this case, the electrons move. So the double bond is actually moving from the top oxygen to the one on the right to the one on the left. So what you have is you have a moving pair of electrons to form the double bond. Now, some of you might say, Mr. Chan, isn't it exactly the same? And the answer is no. They've actually tested it out, and they found that if they had radiated one oxygen, made it radioactive, that the double bond is actually moving. Now, an example of this would be like your hands, and it's good that we have the screen. So if we take our hands like this, if we put the hands together and we overlap them so that the palms are both facing your screen, notice the thumbs are never overlapping. The only time they overlap is if you put one in front of the other and they're opposite, but if they're in the same direction, they will never move. They will never overlap each other. That's the same idea with resonance structure. They look like the same, but what happens is the double bond is actually moving, okay? So if you were to answer this question and draw any of the three Lewis dot structures, let me just get back to Zoom here. Okay, if we share the screen back, sorry. Okay, if you were to draw any of these three here, they would be perfectly correct. Now, when we're doing Lewis dot structures, we also have to consider something called combining capacity. Okay, now, one needs to remember the combining capacity of the element. And generally, the number of bonds an element forms corresponds to the individual element's combining capacity. Now, what do I mean by this? So last day, remember, I gave the example of HPO2, and I gave you the structure, and I gave you the answers like this. So the answer was HOP double bond O. Okay, and I drew it like this, and we're okay. Now, some of you might say, well, Mr. Chan, why couldn't you have done it like this? Okay. Now, if you count, both diagrams technically are correct in terms of the number of pairs of electrons. There's 2, 4, 6, 8, 9. 1, 2, 3, 4, 5, 6, 7. There's 9 in both. But why would this one be preferred? And the reason being is the number of bonds on oxygen equal the charge or combining capacity of oxygen. Now, let me just finish this off. For oxygen, what happens is the charge is -2. So it would like to have a maximum, if possible, 2 bonds. In this case, notice this one, there are 3 bonds. Now, it's not saying that it doesn't exist, but what happens is to reduce the amount of repulsion between the electrons and the bond angles and these things that you talk about in 11 honors, what happens is you prefer to have the number of bonds equal to the charge or the combining capacity of that particular element, okay? Now, if it doesn't work, okay, but if it can, like this, they try to fit it in, all right? Now, one thing about double bonds versus single bonds is this. If we were to look at the distance of the bonds, what happens is here, if you have a single versus a double versus a triple bond, you will notice that the more bonds they have, the closer the atoms are to each other, okay? So what happens is, why? Is because since there are more electrons found between the two atoms, they are actually closer together, okay? Now, what's the significance of this Lewis dot? One final thing, and then we'll call it a day. We can actually calculate the bond energy. The bond energy is the energy needed to separate or release when bonds are formed, okay, like a rubber band. So for an endothermic reaction, energy required is greater than energy released. For an exothermic reaction, energy required is less than energy released, okay? And the units are kilojoules. Now, one can tell the relative strengths of bond by looking at the bond energies, and I'll talk about that in a second. Now we're going to cross this off. So let me say, for example, we had 2H2 plus O2 gives you 2H2O. Now, the question is this an exo or endothermic reaction? Now, so what we do is we draw the Lewis dot structure here in terms of the hydrogens and oxygens. Okay, now, so if I were to take a look at the structure here, so for two hydrogens, it would be, if I broke this apart here, so it'd be H, 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 H. Oxygen would be here. Water, because there's two of them, would be H, O, H, H, O, H. Now, so what happens is this. For this particular question, we look at the hydrogen bond. So on a sheet, I think I've given it to you. You have this bond energy table. So hydrogen is 432. So here we have 2 times 432. Why is it 2 times 242? Is because of the fact that we have 2 hydrogen molecules. Oxygen, I'll do it in a different color. If we take a look at the bond energy, oxygen, O minus, where's O? O, there we go. Right here, 495. So here, it's 1 times 495. And for hydrogen, for water, we have this OH bond. This one here, there's another one here, there's another one here, there's another one here. So there's 4 of them. So it's 4 times OH, okay? Where's the OH? Oopsie, oopsie, oopsie. OH, 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 OH. Where's O? Ah, right here. 467. Okay? So we do that. So 4 times 467. So if we add these up, let me take a look in my, so this would be 1,359 kilojoules of energy absorbed. Here, this one is 1868 kilojoules released. Now, because there's more energy released, here is more. So since this is greater, so therefore, exo reaction. Okay. Now, some of you might say, well, Mr. Chan, I don't get it. Why is it energy released when bonds are formed and absorbed when bonds are broken? Now, what happens is this goes back to your, let me see if I can have this. This goes back to when we went back to bonding. Let me see if I have it here. Okay. Let's see, come on. Okay. Now, if I share the screen, remember we had this particular demo for you. Okay, so let's do argon. So what happens is this. So notice there's an increase in energy. If we look at the potential energy, okay, so if I pause it here, notice from a bond to me pulling it apart, what happens is you have an increase of energy. As the bonds are coming together, the energy is decreased. The energy has been released. So this is why when we break a bond, it's like moving this particle from this low point to this high point. I have to put in energy. When the molecule comes together, it loses that energy. That energy is released. And so this is why, ooh, let me see, do it like that. This is why. So for example, high energy, when they form a bond, it becomes a low energy. To remove these together, if I pull it apart, notice it takes energy away. So this is why what happens is it requires energy to break bonds. And when bonds are formed, energy is released. Okay? All right, that is it for today. Okay, so hopefully you can go through this video again. And what I will do is I will assign you specific questions in terms of the bond energy, Lewis dot structures with exceptions. All right, ladies and gentlemen. So go through that, go through the homework, and then I will go over any problems that you may have next day. All right, thank you very much. Have a good day. Bye-bye.